So in the morning, so I was discussing about one application of magnetic materials which has been revolutionized our data storage and information. I mean, computer, everything is based on basically or started with this technology, this magnetic hard disk drives. Okay, so you saw the presentation of the animation in the morning. So I will share that. Also in the slides, you will find some more material which I am going to discuss in this class. So when we think about hard disk drive, so we want to store as much as information as possible, or as much bits of information as possible in a small density. So we want to increase the density of data, how much we can store in the same amount of volume, magnetic volume. So that actually, so if you look at the number, so in 1950s, so you could store, let's say, 40 MB in a big volume of magnetic disks, and now it goes up to 40, 4, 5, 6, so about 4 terabyte, or now even it's close to 10 terabyte of data you can actually store in your a small hard disk. So the volume has reduced, the price is also reduced, but you can store a lot more information in this magnetic hard disk. So how was it possible? So basically, when you look at your disk, so you can think of it like a magnetic breaks into magnetic domains. So these are basically your magnetic particles. Okay. So this is one domain separated from another domain, and then so you have certain magnetization. Let's say in this direction, this is your magnetization, and here the magnetization is like this. And your 1 bit, so this one represents, let's say, 1 bit of information. And now if you want to store more in the same volume, so the basic, so the first thing is you want to reduce your domain size. So if you reduce your domain size, so domain size, so this is D. So if you want to store, is it visible? Is it visible, the board? No, yes. So it depends on the internet from your side. But I think once this recording is shared, so hopefully you will see that. Okay. So if we want to store more energy, more information in a small volume, so the obvious choice is you have to reduce the size of the domain. So then let's see what happens. So one fundamental thing that happens, which we will discuss now. So what happens to the coercivity when you, let's see, as a function of your domain size. So there is intrinsic relation of coercivity with the domain size, and if you plot that, so I plot here in the y-axis the coercivity, and here I plot the domain size. It is something like this. So this we call a let's say, critical domain size. Okay. So if you are in a normal, like a bulk material, so you have certain cohesivity, but as you decrease the size, so the cohesivity is increasing, right? So as the domains are getting smaller and smaller, the size is getting smaller and smaller, so the cohesivity increases. Okay, up to a certain size called DC, and this size is typically this dimension. It is of the size of the single domain of the material. So if you take any material and you decrease the size of that material, so you will increase the cohesivity until the material itself is in a single domain state. So like if I take this material, so I have domains and domain walls, so it has certain HC, and now I reduce it, so that means, so maybe I have one domain wall, so this is HC1, this is HC2, and I reach the size where I have only one single domain, so this is HC3, and your single domain cohesivity will be much larger than if you have domain walls or more number of domains. Of course, there is a reason for that, so we will not go into the detail, but this curve clearly tells you that. So why it is important to know? Because now, in context of magnetic storage, so what we saw that storage device should have like an optimum cohesivity. Okay, so you cannot have very high cohesivity, you cannot have very low cohesivity. Okay, also it should have a good magnetization, of course, but cohesivity has to be optimized. Otherwise, it will be very difficult to read and as well as write the information. So that's why when one chooses a material for a magnetic storage, so you have to choose it carefully that, okay, ideally if it is in a single domain state, so cohesivity is high, so that is good, and you can work with that. But now one would say, okay, if I want to increase the density further, if I want to put more information in the same volume, so can I continue with that? Can I continue shrinking my domain size or the particle size or my material, the dimension? Can I go on making it smaller and smaller and smaller? Can I do that? You cannot, and this plot actually tells you that. So what happens if you go below this critical single domain size? So again, the cohesivity starts decreasing, and that is not good, because as the cohesivity decreases, so that means it will be easy to demagnetize your sample. So it is easy to demagnetize means then the information you have stored can, due to some, so demagnetization you can do by thermal, it could be due to heat or due to an external magnetic field. So it will demagnetize and you lose the information that you have stored there. So therefore you cannot go below this critical size. And what happens, a very interesting thing happens when you will go below this. So here you see this is actually almost becomes zero, this cohesivity, when you go to very small dimension. So you, I think you are doing this course on nanoscience. So there you would realize that when the objects go to a nanoscale, so they have very different properties from their bulk. Because of their surface area is higher, the surface to volume ratio is high. You have less volume but more surface. And similarly, magnetic properties also differ or change quite a lot. Drastically, they change when you go from a bulk to a nanoscale material. And what you observe when you go to a nanoscale, nanometer range magnet, a ferromagnet. So ferromagnet will go to something known as a super paramagnet. So this is like when your dimension is much smaller than your critical dimension. Okay. So right now, actually, if I talk about dimensions, so I'm just telling some vague thing. So I can give you some number. So now, most preferred material that is used for storage is cobalt platinum with some chromium. Okay, this is an alloy that is now being used. So what you have in your hard disk, this is the material you have, and the domain size in that, which stores 1 bit of information, is about of the order of 10 nanometer. Okay, so this is so tiny, so 1 bit. Remember, so look at the scale. Just imagine, so 10 nanometer has a 1 bit of information. And now, if you go below, even like if you go to 4 or 5 nanometer, so what happens? This material goes into something called a super paramagnet. It becomes super paramagnet. So what super paramagnet means? So super paramagnet is basically like a paramagnet, but it has a very high magnetization. Super paramagnet, so the short form normally it's called SPM. The super paramagnet has very almost zero coercivity. So Hc will be like 0, and due to a thermal fluctuation, so kBt will be of the order of the energy, this anisotropic energy. So what keeps your ferromagnet is the anisotropy. Okay, so that anisotropy basically prevents it from demagnetization. Okay, so higher the anisotropy, better it is. So now, if your thermal energy is of the order of your anisotropy, so then due to this thermal fluctuations, so that means it is higher, or sometimes it is actually higher than the anisotropy. So your magnetization will not stay along the anisotropy axis, but it starts fluctuating. So thermal energy is always there to give randomness to magnetization, to any system. It will give a randomness. So that means your magnetization will fluctuate just like as it does in a paramagnetic case, and it behaves almost like your ferromagnetic material behaves almost like a paramagnet. And if you look, if you plot hysteresis loop, okay, so now if I plot a hysteresis loop of a, so this is my ferromagnet. Now if I reduce the size, what we'll have is something which behaves like a paramagnet. Okay, something very similar to a paramagnet. So there is no coercivity, and it just goes through zero magnetization when the field is 0. So you don't see any repellence or any coercivity, nothing else. And that is definitely not good. So that means if you go below, for example, in this case, below like 8 or 7 nanometer, so it becomes super paramagnetic, and you cannot keep on decreasing the your data density on your magnetic material. So there is always something is called a limit on your bit size. So that is actually one challenge for magnetism, for future magnetic data storage. So there are many alternate, that's why many alternate storage devices are being discussed. Some are based on magnetic material, some are not. But still, it is possible still to reduce the dimension using the same magnetic material, but in a different design. Okay, so we'll not go into that detail. But one limit is this super paramagnetic limit. Okay, so that limits or puts a constraint on what could be the size of your magnetic domain. What could be the smallest bit size you can achieve. So if you go below that bit size, so the thermal fluctuation will take over, will randomize your bit, so you cannot save or store any information. So that's why one has to choose, and that is why this material actually is used, because that still you can make very small, tiny bit. No? That is actually amazing. Now look at this. So you have a 10 nanometer bit. Now you want to read the signal from that. Can you do that with this existing, what I showed in the morning, like a normal induction coil, like you have this electromagnet and you have the coil around it. Can you see the signal from this tiny magnet? The answer is no. Okay, so you cannot do that. So it is not easy to just use a normal, like like electromagnet, and read the magnetic signal from that. And that's why new technologies were developed. I mean, so the development of this sensors, okay, magnetic sensors, happened really in a different way, but they are actually used quite a lot in reading this magnetic information. So how you read it? So like you saw in the morning animation, so you can read it by using this technology is called magneto resistance. Okay, so it is called magnetoresistance. So this is another technology. It is primarily developed, really working quite well because of something called a thin film technology. Okay. So what you can do in thin film technology, you can prepare. So if I take a substrate, so I have a substrate. The substrate can be like a silicon wafer, for example, you can take, and I can deposit a film on top of it. So this is my thin film. This is my substrate. Okay, so I can deposit thin film on a substrate, and this is then I can measure the resistivity or resistance of, for example, in this case. Okay. So again, the thin film will have a very different properties from a bulk material itself. Okay, so that is again another area of research. Some of you might do it in your project in future. So what happens, let's say, in context of magnetoresistance? So if I take a thin film, so let's say I have a thin film. So this is now thin film, and now it has certain magnetization, and I pass a current through it. Okay. So the resistance in presence of field. So I apply magnetic field H. So whatever the resistance in the field H is not equal to when the field is 0. So this R0 represents, let's say, the resistance when the field is 0, and now I apply a field, and the resistance will be different. So now you all know about Hall effect. You did that experiment. So now, the Hall effect is basically when you apply a magnetic field along this direction, perpendicular to the film plane. Okay, so if it is in the z-axis and you are passing a current along your x-axis, so you will have a Hall voltage which will develop, and you will have a Hall coefficient and so on. But here this is different. Here we are talking about, so there is a change in resistance, and this depends on the angle. So let's say if I apply a field H in plane, okay, it's not, I'm not applying a field perpendicular to the current, but I'm applying a field in plane. So you have certain angle theta, and this resistance depends on angle theta. Okay, so this is called anisotropic magnetoresistance. Okay. The short form is AMR. So when you do actually, in sensors, AMR sensors, they exist, and the sensitivity normally will be calculated by how much resistance change happens due to the magnetic field. So this is like you observe like 2% of change or 3% of change. So this change in resistivity due to the magnetic field will be very small, but still you can detect it by your like some signal and amplify it and so on. You can detect it, and that works quite well. But it is still not good enough to detect a magnetic the magnetization of your tiny 10 nanometer magnet, your domain. So for that, what people use is something called giant magnetoresistance. Okay, so short form is GMR. Okay, so what is a GMR? This is another sensor, another kind of sensor. Again, I mean, these things what I'm discussing can be useful for you are thinking about your assignment, team assignment. Okay, so what is a GMR structure? So it is a different structure, again a thin film structure. I take a thin film. The thin film is normally the thickness would be, so thickness would be like maybe 10 nanometer or maximum I would say up to 100 nanometer. So not more than that. So these are I would call a thin film. So in this I have 3 layers. Okay, so I have 3 layers. So this is a non-magnetic layer, and these 2 are magnetic. So you have either magnetization like this, or would be like this. Okay, so these are the possible magnetization. I mean, not it could be like this, or can have certain angle. So this is basically, so it's a magnetic layer. So bottom layer is magnetic, top layer is also magnetic, and they are and the non-magnetic layer is sandwich. It's like a sandwich, right? So you have a non-magnetic layer, top and bottom you have magnetic layer. So now if you measure the resistivity, so you pass a current in this direction, perpendicular to this. Okay, so this is your thin film, and you are passing a current along this. So you will again observe a change in resistance. Okay, this RH will be different from what when you have no magnetic field. Okay, so now you can measure the magnetization. In fact, the most interesting thing is, so the resistance actually depends. So you are passing a current. So the resistance depends on what is the alignment of these 2 magnetization now. So if you have an arc like this, so this is, let's say, when they are parallel to each other, it will be less than when they are anti-parallel to each other. So if I have magnetic, so this layer has a magnetization opposite to this, the bottom layer, so I will have a higher resistance. So now, so how is it useful to detect a magnetic field from domains? Okay, so now if I put a small domain or something, a magnet here on top. So if I put a small, this is my N, this is S, okay, so this is N. So if I put a magnet like this, okay, so this has some certain field, magnetic field it is going to generate. And then, so what happens in typical this GM magnetoresistance devices, GMR devices, so typically you put this magnetization will be very, or the coercivity will be very high. So that means this is called a fixed layer. So the bottom layer is a fixed layer. That means you cannot rotate the magnetization in this layer. And the top layer is a free layer. Okay. So free layer means this magnetization is free to rotate along any direction. So now if I bring a magnet close to it, so this will react to that magnet, whatever the magnetic field is, and it will get aligned along that magnetic field, right? So if the magnetization is either it could be, so depending on it could be at certain any angle or parallel or anti-parallel, depending on what is the magnetization here. Okay. So now, if I am passing a current through it, and at the same time I bring this magnet, so depending on the orientation of these two layers, so I will have different resistivity, right? So let's say R will be not equal to R like this. So if I can detect what is the resistance, and then I can say, so I can plot, let's say, resistance as a function of my angle theta. So this is the angle between this and your bottom layer, and basically this angle is defined by what is the magnet that you have put. So I will have, so when they are parallel, that is the resistance is minimum, okay, something like this. I'll get something like this, okay. So this is, let's say, 180 degree, this is 0, and this is again 360 degree. Okay, so this is how the resistance will vary, and so then depending on which part of the curve I am, so I can able to tell what is the magnetic signal that is here, the magnet that is producing the magnetic signal. So I can do a calibration and I can tell that. Okay, so this is how this GMR devices work, and right now even this layer can be changed to a, so this can be metallic, this can be insulating. So there are different terms for that. So we will not. So I'll put it in the slides and share it with you so that you can go through that. And then we stop for today because it's already 2:30. Okay. And in the next week, so we will be done by Tuesday. So that is the last class. So we have 2 more classes, and the next week we will discuss about superconductivity, because that is a very fascinating field you should know, and we will devote 2 classes.